Olá, gente, sejam todos bem-vindos. Desculpa pelo horário inusual. Hoje temos a grande honra de ter conosco a professora Catalina Curceanu. Ela nasceu em Transilvânia, muita gente aqui conhece pelo Drácula, ela nasceu mesmo muito perto do castelo de Drácula. Fiz o doutorado em física na Universidade de București, na România, trabalhando na física de partículas, mesones exóticos, na colaboração Obelix do CERN. Do CERN. Depois ela iniciou a trabalhar no experimento SIDDHARTA. Depois ela se mudou para a Itália, onde ela ainda está, no Laboratório Nazionale de Frascati, perto de Roma. Trabalhou no experimento SIDDHARTA 2, onde ela foi a porta-voz, a spokesperson, sobre Chaonic Atoms. E depois ela virou uma das líderes, iniciou a ser interessada e virou uma das líderes do argumento que nós vamos falar hoje, que é verdadeiramente muito interessante, só para estudantes. Quando você aprende mecânica quântica, a causa do fato que tem um formalismo matemático muito esteso e bastante abstrato, a gente entende isso como uma espécie de, semilinguagem religiosa. Olha, é assim, operadores hermitianos, autostatos, etc. Mas, no fim das contas, são leis da natureza. Exatamente como todas as outras leis da natureza, da física, são suscetíveis à falsificação experimental. Isso aqui é o argumento de que a professora Curceanu é um líder e que está investigando. Ela iniciou a usar o experimento VIP2 para fazer teste do princípio de exclusão de Pauli, sabe? Parece uma das postulados básicos da mecânica quântica, mas é uma coisa que pode ser testada. Ela pegou uma bolsa do John Templeton Foundation, Foundational Questions Institute, para uso dos experimentos da física de partículas, experimentos da matéria escura, que mesmo muitos de vocês estão trabalhando para testar, isso é coisa de testar fundamentos de mecânica quântica. Ela ganhou o Emmy Noether Award, o Betty Moore Foundation Innovation Award, e também virou cavaleiro, o rango do cavaleiro da República da România. Como sempre, vai ter lista de presença no chat, eu vou mandar o link no chat. Por favor, se não tem questões urgentes, espera até o fim da palestra. Professor Curceanu, thank you very much for speaking to us, and you can start.
Thank you very much for inviting me to give this kind of, seminar. Let me, since we are not so many, if you have questions, even when I'm speaking, just stop me and ask the question. It's perfectly fine, so we can just have a chat. So it's a pleasure to present you the research we are doing in the field of quantum physics. And my group, it's an experimental group. I'm going to show you what are our research from experimental point of view of questioning quantum mechanics and trying to uncover, if any, some violations of some fundamental principles in quantum mechanics. Before going to do that, let me first add something about myself. So you have heard I was born and grew up in Romania, actually in this beautiful town, which is called Brașov, which is very near. That's the town itself. It's a very nice town. And it's near the mountains, near Carpathian Mountains, and near this castle, which is the original one of the one which in the movies is more shown like this, because it's of course the so-called famous Dracula castle, but of course in reality there is nothing like that, but some kind of inspiration which came from a person who was a king, Vlad Țepeș, who is a very, very positive figure in the Romanian history. However, I'm not here to talk about history, but I'm here to talk about physics. But just as a joke, of course, that who is born in such a strange place near Dracula Castle, what can be involved on? Well, I'm working on this zombie cat, namely the Schrödinger cat paradox, a cat which is alive and dead in the same time. And I'm going to come back to this because this is one manifestation of the so-called measurement problem in quantum physics, which we are trying to work out a possible solution from experimental point of view. And before going to do that, the other part of my activity, which I'm not going, however, to speak about, it's related to nuclear physics experiments. Right now, I'm in my office, which is right here, where is my pointer. And this is very close to this accelerator, which is called Daphne, where we are studying nuclear physics. And we actually, our institute did never close, even in this pandemic period. We are working inside, that's inside picture of this collider, electron-positron collider, which is delivering the phi resonance, which decays in charge kaons, which we are using for actually studying exotic atoms, namely kaonic atoms, negatively charged kaonic atoms, to understand the QCD in the strangeness sector. That's part of my team in 2019 when we installed our experiment called SIDDHARTA 2, which is measuring X-ray transitions from kaonic atoms to try to measure strong interaction at very low energies, which it's also relevant for a better understanding of neutron stars and of the ansatz that in neutron stars, there might be some strange matter in their heart. So that's kind of neutron star, very, very interesting objects, very dense. Presently also gravitational waves are being measured. And our research is also contributing to understand if inside to the equation of state, there is a contribution coming from strangeness. What I'm going to tell you about today is not so much nuclear physics, which that was all what I was going to tell you about. Actually, it was a difficult choice whether to tell you about nuclear physics or about quantum physics. However, we decided together with the organizer to focus my talk on this very, very interesting research which we are experimentally performing in the underground lab of Gran Sasso, so my lab is here near Rome, but it's here in Frascati, so we can reach Gran Sasso about 150 kilometers pretty easily. That's a very nice lab. It's not really underground. It's more like under mountain, where very, very different experiments are installed, mostly for studying dark matter, neutrino physics, and in our case, also quantum mechanics. So it's clear the reason for actually installing a lab underground, which is due to the fact that you are studying, as also in our case, so rare events or even potentially non-existent events where you only put constraints, that you don't want to have all these, let's say, events which are generated by cosmic rays. So that's the very reason for which many research in this sector is being done underground, either in X mines or, as in this case, under the mountain, where the cosmic ray is reduced by 6 orders of magnitude in our case. We still have problems with environmental background because there is still radon or let's say, daughters of nuclear decays coming from radioisotopes present either in our setup or in the rocks of the mountain. It's really a very beautiful and impressive lab, which is located in a gallery where cars are circulating and they commute between two towns, L'Aquila and Teramo. And halfway, more or less, in this 11-kilometer long gallery, there is the opening towards this, as I was saying, very big lab, which is hosting big experiments devoted to all this type of extremely rare events or potentially non-existing events. That's the entrance where only authorized people can go. And that's, well, a picture from inside, where there are 3 very big galleries and more smaller experiments hosted in this kind of barracks like our own. That's myself, according to the electronic engineer in my group. And what I'm going to tell you about in what comes next, it's our research in the framework of the so-called collapse models, and very briefly towards the end of the Pauli Exclusion Principle violation. They are somehow connected with gravity in very different ways. I anticipate the first one, it's kind of connected with gravity, starting with the ansatz that gravity cannot be quantized, while the second one is the other way around. It assumes that gravity can be quantized, and one of the things which might produce, it's a violation of the spin statistics. That's part of our group in the Gran Sasso underground lab, together with our setup, which you can see it's small, so you don't need big apparata to study interesting and nice physics. And that's last year, where by the way, you can see not only that we wear masks, but what you can see is that here the setup was only started to be installed, while here it's completely surrounded by lead and copper, which are required. It's ultra pure lead and copper are required to shield the apparatus from the residual background, mostly coming from decays of rocks, uranium, and all the chains from the rocks and from the underground. And I'll start by speaking about what we do in the framework of the collapse of the wave function, which is related with the Schrödinger cat paradox, which probably many of you, if not all, already know, which it's a manifestation brought at a sensible level of a cat being in a superposition of state, dead and alive, the cat closed in the box with a nuclear source, which is the quantum object, which has a probability of 50% to decay and 50% to remain not decayed in a certain amount of time. The decaying source produces radiation, triggering a hammer, breaking poison, which would kill the cat in case the source decays. And this, I'm not going to speak any further about this, but however, this it's a manifestation of the so-called measurement problem, which actually goes like how one actually goes from a superposition of states, which is typical to quantum mechanics, to the collapse of the wave function, which is what you are measuring when you perform a measurement, which in standard quantum mechanics, it's resolved by a kind of a postulate. So there is a measurement postulate, there is no physics inside, so there is nothing of physics which triggers the collapse, if any. And many people are unsatisfied, not happy with this solution. So they're trying to work out, unless you're a Copenhagen, so unless that, when you believe that physics might not necessarily describe reality and should not describe reality, then you don't care that it's a postulate. But if you assume that physics is dealing with some sort of reality, you are not very happy about this, so you try to look for some solution. And solutions and interpretations are quite many. Some are very, very interesting, like the many-world interpretation, which assumes that the answer is that each time there is no collapse, actually. The wave function, it's a real object, and then you have to take for granted that whatever happens with the superposition still stays there. So this divides in many worlds. The other one is de Broglie-Bohm, which relies on an ontology of particles. So there are only particles. Then you have to kind of associate a wave, which is not really a material wave, but anyway, so there is some mathematics inside. However, the first two ones are interpretations. The third one on which I'm working, because as an experimentalist, I like to measure something, it's not an interpretation, but it's a kind of a modification. So you modify quantum mechanics, and as such, you find a completely new phenomena. And as I'm saying, these collapse models are rival theory of quantum mechanics in such that they modify the quantum mechanics. Of course, if you modify them, you expect to have a different phenomena. So you expect that you can envisage experiments which are testing them. So then further on, you can assume that the collapse might have something to do with the only thing which we did not yet succeed to quantize, namely gravity. So you might find a reason for collapse which could be related with gravity itself. So as I was saying, what actually these models are doing, they are cutting the problem from the root. So the problem of the collapse, it's dealing with the linear structure of the Schrödinger equation. As long as you have a linear equation, you can't get rid of the superposition. So a solution from here is you introduce nonlinear terms, which are parametric. So this is not a fundamental theory, but it is an effective theory. As such, you have parameters. And the first models were proposed already in the 60s. I'm not going to show them to you, by Karol Házy in Budapest. They have been worked out later on by Ghirardi, Rimini, and Weber and Pearl. And even later on in these papers, where there is this continuous spontaneous localization model, where you introduce this additional term with respect to the standard ones, which are non-linear terms, which you need to choose, however, carefully, because you want to preserve whatever you know and you measure, namely quantum behavior, interference of single electrons, and so on and so forth. But you want kind of to get rid of the superposition for macroscopic level, with a transition which is smooth between quantum behavior for one single small number of particles, which can go on very long in time, and you want to get rid of superposition in very, very fast time scales for macroscopic objects. So what has been proposed, it's a realization of these models with this type of operators. So you have these new terms which are parametric. I'm going to comment on them briefly. So they are nonlinear, and moreover, they are stochastic, because you have to preserve what you know from quantum mechanics. So the collapse should kind of respect the Bohr rule. And what are these parameters, which are called the collapse strength? It's the, let's say, a kind of a rate under which the single particle is collapsing. So I have to add here that for a macroscopic body, you have an amplification factor of the collapse, which goes with the number of particles in the body. So for an Avogadro number of particles, even a single particle which is collapsing, it's triggering the collapse of the whole body. So even if for single particle, the collapse, you will see the time scale, it's occurring after ages and ages in a time much longer than universe lifetime up to now. When you have an Avogadro number or a big number of particles, the collapse is nearly instantaneous. And the other parameter is the so-called correlation length, because the wave function is, yes, collapsing in one of the possible outcomes in the superposition, but it's not collapsing in a delta function. It collapses in a kind of a Gaussian centered with this correlation length around one of the positions. It's a collapse in position basis. And this kind of rate of the collapse, so how fast a single particle is collapsing, has been received. So these are the proposed values for the parameters for the lambda parameter, which has been received very different values. So proposal for values. One, the original proposal of Ghirardi, Rimini, and Weber is like 10 to minus 17, the rate of the collapse, which means that a single particle stays in a superposition for ages which are 10 to the 17 seconds, so ages and ages. And the second proposal, which has been put forward by Steve Adler, it's kind of much more optimistic, better for experimentalists, because it's 10 orders of magnitude higher. And that's related to actually the fact that there is a mesoscopic world where we do not know yet, because we were not yet able to perform interference experiments to check whether they behave quantum or not in this mesoscopic land, even if somehow the Vienna group is doing better and better, so towards arriving to more tests to check whether mesoscopic bodies and molecules are still behaving quantum or not. So I have to tell here that what you would expect would be that at some point for a big number of particles, if you would be able to do interference, like interference with tennis balls, and you would be sure that you isolated them well, you expect to see in certain conditions interference if the models, if collapse models are right, you wouldn't see interference any longer, but not for effects which are going like decoherence. So it has nothing to do with decoherence. Decoherence is not an answer to the collapse of the wave function. You wouldn't see interference because of this interaction of the particle with an external field which cannot be quantized. That's why people might have assumed it's gravity. And this induces the particle to collapse in one of the possible outcomes, one of the possible solutions of the superposition. Now, since you are unable to do experiments with tennis ball in trying to put them in interference, and since the limit you can get from interference leaves open tens orders of magnitude here, there is another way you can test these models, which kind of...
I'm sorry, Catalina, since you said that we can ask questions in the middle, just to understand, I mean, physically, decoherence is very different from spontaneous collapse, but you said now that it's also experimentally distinguishable.
If you are sure you don't have decoherence there, so if you can get rid of decoherence.
I see. Thank you.
So decoherence, it's an answer for any practical purpose, but it's not an answer to the collapse of the wave function from the root. So decoherence, it's leaking the superposition in a bigger system. So that's the reason for which it can't get rid. It gets rid of superposition for your small system, but it leaks the superposition in bigger and bigger system. So it doesn't solve the measurement problem. However, if you want, that's the very reason for which it's very difficult to do interference experiments with bigger bodies, because it's very difficult to get rid of decoherence. So when experimentally you go there, getting rid of whatever decoheres your wave function is becoming exponentially more difficult with the dimension of your body. So that's the reason for which, if you want to be sure you don't have decoherence, but you measure the collapse, genuine collapse from this type of model, it's very difficult experiment. So it takes a long way to get to do that, assuming you will be able to do that. But there is another way to measure that, which is the one we use actually in Gran Sasso. So when a charged particle it's interacting with this collapsing field, I'll call it field or noise, but don't leave you to be misled, because field doesn't mean it's quantized. It's something, it's a noise, it's an external entity which is inducing the collapse, but can't be quantized, because if you quantize it, you are back to the root. So you are in the framework of quantum mechanics, while here you want to go out from the framework of quantum mechanics. However, if you have a charged particle interacting with this field is always shaking the particle. So a charged particle in this condition would emit radiation. This radiation would be, for any practical purpose, a spontaneous radiation. And if you want to ask me, doesn't this mean a blasphemy, like energy is not conserved? I will answer to you, yes. Indeed, in these models, the emission of spontaneous radiation, it's a phenomenon which does not conserve energy. That's why it's called spontaneous. However, who is working in these models is not really worried about this phenomenon for two reasons. One, because these models are not fundamental models, so one might expect to cure it when you know what's the fundamental model. And secondly, because there are even ansatz that the missing part would justify somehow the dark energy. So there have been put forward some timid tentatives to connect the part in the visible universe. So what is the spontaneous radiation in our visible part of the universe with a gap closing in a dark energy. However, that's not my task. So I am mentioning this only to tell you that if you have had the hint that this does not conserve energy from our standard model, it's right. But we are not in the framework of the standard model because actually we are just cutting at the root, one of the pillars of the standard model by modifying quantum mechanics. That's the radiation we are measuring. So you would expect for an isolated system which does not emit and it's, let's say, isolated from the environment, you'd expect that this body emits radiation. And this radiation should not be cosmic radiation or radioactivity from the body. No, not at all. It should be this spontaneous radiation emitted by all charged particles which are all the time interacting with this noise which is collapsing the wave function. And this has been worked out since the formula, a very first formula has been worked out in the end of 90s. It looks like emission of radiation goes, it's 1 over energy with parameter lambda, which we want to constrain. And the radiation is very faint. So if you want to set sensible limits to the radiation, of course, even in my office here, I can measure radiation. No doubt I can, and there is plenty of it. And no doubt I can put limits on this model, but my limits are extremely lousy, so are very bad. They don't come any closer to the limits proposed by Adler and Ghirardi, Rimini, and Weber. So it's obvious the limits I can put in my own office are garbage. So if you want to really constrain the model, you have to work in very clean environments, meaning experiments underground. And before doing our own experiment, we have actually reanalyzed some data from another older collaboration, which is IGEX, which has done a very nice data taking with this germanium detector. We have analyzed their data just to check whether it's worthwhile to go and set up an experiment, because our experiment wouldn't have been infinitely better than theirs. They already have done a very great work. And with our nice surprise, we arrived at the conclusion that with a Bayesian analysis, on their spectrum, with a fit on 1 over energy, we could constrain the lambda parameter. Actually, here you might see the plot in the lambda RC. So the values I gave are with an RC 10 to minus 7 meters, for which these are these 2 limits which I showed you before. However, there is no necessary reason for which you might take for granted the collapse, it's a Gaussian with 10 to minus 7 meters. You might open up a bit this, and if you open up this, you open up the lambda also, because they scale together. So you put limits which look like this, and already what we can conclude from our measurement, which has been published some years ago, we could already conclude that we can discard all models because we go beyond the limit of Ghirardi, Rimini, and Weber. So all models which are not having a mass dependence can be discarded. What does it mean? It means that if lambda is a parameter, it depends on the particle type. So the electron has its own, the proton has its own. There is no universal collapsing frequency, which sounds reasonable because whatever else it's depending on the mass. So this sounds really reasonable. So we ended up with this, let's say, with this curve. So we excluded Adler, but we are still some orders of magnitude. We were actually far from Ghirardi, Rimini, Weber. Since then, it happened few things, because once we verified it's worthwhile to go in this direction, we have done two things. The first one was to identify not only a generic model like CSL, I told you before, where you might imagine whatever noise in the universe which is collapsing your wave function, but we went for the so-called Dioggi-Penrose gravity-related collapse model, where to identify the reason for the collapse, it's gravity. And this goes somehow in the following sense, that you assume in this case that you have, let me, okay, no, go back. So in this case, the things go like that. So any superposition in space of the wave function, it's also a superposition of two geometries, space-time geometries, taking into account the general relativity. So two superposition of space-time geometries, and this, since gravity can't be quantized, somehow gravity doesn't like this, and the wave function, it's collapsing as a back reaction from space-time. So there is a collapse in this case due to the fact that you don't have superposition, you can't have a superposition of two space-time geometries. And there are two visions here. One is the one belonging to Penrose, who proposed this idea, but he doesn't have a dynamics for it. However, Lajos Diósi, who's the other one who worked on this model, he has a dynamic on it. Dynamic, it's not so complicated. I mean, it has elements of complications. It's the so-called Schrödinger-Newton equation, where you make a kind of equation Schrödinger, where you take the Newtonian potential into it on board. And the wave function is collapsing in a time scale which depends on the mass of the bodies. So this is the energy scale in which it collapses, where you can calculate it. I'm not going to give details. They are in our papers, which I'm going to cite. So here it's involved the superposition of the wave function from the two space-time positions. And you end up, for what we are concerned, out of a bit of calculations, which in our case have been done from the Trieste group of Angelo Bassi, together with Sandro Donadi and with Lajos Diósi himself. It also predicts, since that's the phenomena very similar to what I told you before, it predicts, since particle, it's always in a superposition of space-time geometries, the particle is jiggling, and you also end up with a radiation emission, which you can compute the rate by this Lindblad equation, which again, I'm not going to pass through. But however, it's so that's the equation which you start with, where you have nonlinear terms, and you end up with a formula for the radiation rate in this case, which looks like this. So you have a cutoff parameter. That's what I told you before. You have a superposition of two space-time geometries, and particle is jiggling due to this space-time geometry emitting radiation. And in this case, you have a cutoff parameter, and the radiation rate looks like this formula, Diósi-Penrose, the photon rate, which is shown before. So which means that for this very specific model, by measuring the radiation, you can also constrain this specific model. You can also constrain the other one, of course, the CSL, but you can constrain even more. You can constrain these gravity-related collapse models. So at this point, we have performed our own dedicated experiment in Gran Sasso, and we published, this is the paper in Nature Physics, appeared online last year, on print this year, which we had the surprise to be on the top 10, actually on the second place, most interesting article found by favorite articles, non-COVID related, of course, in this website, which I'm citing here, of All Sciences 2020, which was very nice surprise. So that's the experiment. So we have here, you don't even see our ultra pure germanium detector because it's closed in this case of ultra pure copper and lead, but you can see it here in this drawing. So we have a germanium detector surrounded to shield it with layers of coppers and lead. And we measure the radiation emitted by germanium itself, so this radiation which is supposed to be spontaneous, and by the surrounding materials. We derive the rate of this radiation, which looks like this. So that's the radiation we have measured. And this radiation we have measured, we considered for analysis the range between 1 and 3 MeV. So we have performed our analysis in this energy range with Bayesian model. And we arrived at the conclusion, that's a lot of analysis details here because we have measured kind of 500 events, but not all of them. You might see here, there are two obvious peaks, which are due to the cobalt transition, which we know can't be coming from the collapse. So they are, in spite of all the care we put in purifying our materials, there are still residual radionuclides. But that's okay, because this helps us to Monte Carlo our setup and to assign part of these events to background. So not all we measured, it's of unknown origin, so potentially collapse models. Part of it, it's obviously related to its background, which we were unable to get rid of. And when you take into account the part of the background, you end up with this parameter, which it's related with the gravity induced collapse. And this is very, very interesting. So this is our parameter, which we constrained, which actually it's an order of magnitude smaller, the one which was supposed to be predicted by theory, than the one which we succeeded to constrain from our experiment. So that's the parameter put in the theory by Dioggi and somehow also by Penrose. If you assign to Penrose model the dynamics of Dioggi, and the models which, the limits which were set before could not reach this, so was a viable model. We got an order of magnitude bigger, so we excluded this model from in its simplest version. So we succeeded, that's why it makes kind of a fuss, the article, because we excluded this model. For sake of true, I have also to tell you that Roger Penrose doesn't like this radiation. So right now he's working out a model where he would like to get rid of radiation, so not have at all radiation. But for the moment, he's still working on, and the only way he found to try to do that, it's back in time reaction, so backward in time. So he's trying to work something on that. But if you assume that there is no action from the future, you stay with this radiation, and that's the status today. What does it mean? So it doesn't mean at all that gravity does not play a role in this context. It only means that the simplest model is excluded, which also means that you can start to do the real work right now. So you can start to do more realistic models, which are memory, so Markovian models, and where you can take into account a more complex dynamics, which is very interesting. So that's what we are actually trying to do right now. We are improving our setup and also our theories. You can also say something more about the other models, CSL. And what we are doing right now is we are coming with our analysis orders of magnitude better than our limit before. So that's our limit here. And we have a paper in preparation. So that's what we gain here. We are still not 10 to minus 16. That's still a way, a lot of work to be done to go there. Okay, so let me jump. That's one of our, let's say, workshops where we were discussing this issue. You might recognize here Roger Penrose and also the HPGe. This has been in 2019. Last year, we couldn't, I show you, we only organized online version. And this is very interesting because it encourages to think what's the role of gravity, if this has anything to do with a hidden dark sector, and if there is any theory beyond standard model. And that's a workshop where we restarted to discuss these items in December. That was online, where Roger, you might see him here, has presented his new ideas about this model where back in time reactions might try to get rid of the spontaneous radiation. So it was very interesting. And yeah, so that's what we are trying to do. It's kind of trying to understand how to go from to be and not to be Schrödinger cat to the to be or not to be the famous sentence. We also have related this, I'm not going to speak about it, an FQXI project started last year, which you might know that the Penrose model of gravity collapse, it's also at the basis of this model, orchestrated objective reduction model for the consciousness. So we are investigating this in the framework of this ICON project funded by FQXI. For some minutes, I want also to tell you something about the other research we do in Gran Sasso, which is a search, experimental search for violation of the Pauli exclusion principle by using atomic physics. Of course, everybody knows in this community that in principle, in nature, there are realizations of either symmetric or antisymmetric wave function. This is related with spin statistic theorem, which has been proved starting with some postulates. And if you want to violate spin statistics, you also need to violate some of these other ground of this beautiful theorem, like CPT, locality, or it might also be related with non-commutative space-time. I'm insisting on this because this is somehow embedded in many beyond standard model physics, the non-commutative space-time geometries, like, for example, in some quantum gravity models, which we are working on together with some theoretician colleagues. So in some of these versions, you are expected and predicting violation of Pauli exclusion principle. So what we do actually is we look for atomic transitions prohibited by the Pauli exclusion principle, like copper, where we circulate an external current just to have these electrons to test this violation. And we look for atomic transition bringing the one electron as a third one on the fundamental orbit with an energy which is different from the normal one, very, very singular. So if you see, in this case, it's not continuum, but it's a signal. So you have a clear identification of the transition, if any. And we have worked quite a lot on this experiment. So we circulate a current in a copper strip, and with X-ray detector, we measure the signals. This is a paper published in 2018, just to show you kind of our methods. So we have no current, which we use for background, and with high current, which we use for signal. We do analysis in parallel, and if we see nothing, we set a limit on the probability. So the probability we found in a certain treatment, it's probability for violation around 10 to minus 30. And the theoreticians with whom we are working are from Shanghai and from Fudan. Now he moved to another university of Italian origin, and they work also on the theory, preparing and producing models which are actually foreseeing violation of Pauli exclusion principle, starting from non-commutative versions of space-time induced by Lorentz symmetry and of this kappa K Poincaré and theta Poincaré, which are entailing violations on this type of scale, so very, very small violations. And if you want to learn more about this, we have published, 3 years ago, an extensive paper in CERN, Courier, where we explain reasons and motivation and history of trying to put the Pauli exclusion principle on trial, because we are not the first one who has done that. And so that's for the second part, that research in underground laboratories, it's extremely, extremely, extremely interesting because it allows to make accurate tests also not only of dark matter and neutrino, but also on quantum mechanics. And one of the things, by the way, which I didn't include here, but it would be very interesting to study, is, as in many other searches, to do similar tests in a southern hemisphere. So right now we are in contact with Australia. They are setting up an underground lab, but maybe in Brazil one can try also to do something of this type in one of the mines. The experiment is small and very manageable in this case, because there are features which you might extend your search by doing the experiments in 2 hemispheres, where you can get and learn, of course, something more. So that's the financing, our financing boards going from FQXI, Templeton Foundation, national and international projects, including European projects, which I didn't mention, but it's also very interesting. We try to measure same kind of radiation with optomechanics. So we have an experiment where we try to measure departures from noise due to additional heating, which comes from the same source as our radiation we try to measure in underground labs. So that's the testing large-scale limit of quantum mechanics. So thank you very much. With this, I kind of finished my talk, leaving space for if any questions. Thank you very much.
Thank you. Thank you very much for a great talk.
Thank you.
Any questions? While we wait, I have a simple one. So what difference will the southern hemisphere make?
There are, so for what concerns the Pauli exclusion principle violation, there are some hints that you might have this type of non-commutativity, which depends on where you are on the space-time. So you want to check, if you would measure the violation, you would want to check, of course, if you measure nothing, you measure nothing. But if you start to have hints that there is some measurement there, it might depend, since it's related with space-time geometry, it might depend on the position, or at least that's the idea behind.
Like a preferred direction.
Like preferred direction, exactly.
Yeah.
Exactly.
Other questions?
Hi. I have a simple question.
Hello.
Yep. Can you hear me?
Sure.
Hi. Actually, I was quite excited by your talk. Very nice. And I have a simple question also related to the collapse. I worked with the Ghirardi-Rimini-Weber collapse model, and although I like it somehow, but I don't quite understand how it actually is different from decoherence programs. And instead of working with decoherence, which I believe it's quite has a very nice, development. I know that Ghirardi-Rimini-Weber works with real decollapse, so you actually have a selection of a result. I wonder whether would you consider, for example, some model that instead of having a collapse, you would have a decoherence instead? And if this would be better to describe your experimental results?
Thank you for the question. Actually, this helps me to kind of clarify, or at least try to clarify, because in the decoherence models, you don't really expect spontaneous radiation. So if you do interference, you expect interference to die away. You don't know it's what. So decoherence for any practical purpose solves the problem, but it's not solving it at the origin. So it doesn't get rid of superposition. Superposition leaks in a bigger space. So you stay forever with the superposition. In your limited, however, system, it looks like the wave function collapsed. But however, the real difference between the two, it's in interference experiments, if you are not absolutely sure you got rid of decoherence sources, which might at some point be also the cosmic microwave background, you can't be, you can't be sure whether, you can be if you control everything. And if you still see the interference dying away, there is something more with respect to decoherence. While in our case, the spontaneous radiation, which it's really a trademark of dynamical collapse models, because you have particles which are jiggling where you don't expect them to jiggle. So there is no reason for which they should emit radiation in the decoherence model.
Well, this is actually nice that you mentioned the cosmic background radiation, because somehow almost 20 years ago, we have, me and some collaborators, we put a paper which was similar in fashion to the Ghirardi-Rimini-Weber model, but instead it was more related to this decoherence problem, because we considered that a very naive model from my point of view, that at the beginning of the universe, the radiation, the universe was very hot, and the radiation interacted with the ionized matter. And in that form, the radiation, this cosmic background radiation, was the responsible for the collapse, or for the decoherence in our case, because it would act in this in the center of matter of the system, inducing the decoherence, and therefore the universe is cooling off. So that's why we don't see this anymore in the present physics, at least at this rate. So I wonder if it would perhaps this would help somehow to understand, or if it's perhaps it's a nonsense theory.
I don't know, I'm not an expert in theory, but I assume that at least in our case, where we are looking for X-rays of energy infinitely higher than the microwave background radiation, that wouldn't help. It's clear that if you look for decoherence in any way and in any mean, at some point in interference experiments, that's a limitation. As it might be, by the way, interactions with the dark matter particle, assuming they behave quantum, and you don't know them. So that's another source of possible decoherence eventually. That's an interesting, these are very, very interesting actually issues, because they are going in parallel. So decoherence, it's embedded fully in standard quantum mechanics. So you need nothing new. It's decoherence, and that's nothing else you need. But decoherence, as was always pointed out, it's absolutely not solving the measurement problem. It survives. So you have a superposition of state, but it's expanding to a bigger system which you don't have access to. So only God can see the interference at that point. You don't, because it leaked far from your lab.
Okay.
You are muted. I see you.
Yeah, I have a sort of follow-up question about this. That one thing I learned in Campinas, because there are people such as Marco Cesar who worked on this for a long time, is that if you put this stuff in a quantum field theory setting, the amount of coherence and the frequency of the interaction are related in a very non-trivial way. I know that in condensed matter systems, you have examples where you have very soft radiation. You have very soft radiation, which causes a lot of decoherence. There is a fixed point, and if you study very particular systems, I mean, this is not necessarily. I mean, the question to you, this is an experimental question, not a theory question. I mean, the model that you guys falsified is very quantum mechanical. It's not really field theory, right?
No, it has elements of field theory when you start to calculate.
When you start, okay. My question is, and this is sort of an experimental question, is there sort of, aren't you guys worried that there is frequency cutoffs in your experiment, that there is soft radiation which would be undetectable to you, for example, which could cause decoherence?
Not in our case, because we are far too high. We are gamma radiation. So in our case, we are far too energy. It's a problem eventually for the optomechanic devices, which are getting also that very, very, very long wave function radiation, whether they are able to get rid of all sources of noise. But your question is interesting from another point of view, because right now we are working at models, which, as I told you, are not the simplest ones, but they have Markovian and diffusion effects and dissipation effects, because dissipation is something you would like to have inside. And they might have a shape which is not like 1/A I showed you, but might have complicated shapes. Yeah. And there it becomes very interesting, because in that sector, it might be completely different if you look into optical radiation or if you look into gamma ray radiation. So you have cutoffs, and you're right. So there are cutoffs, because otherwise you run to infinity.
I mean, the decoherence part, I mean, the thing that you get rid of could have singularities at the infrared. Let's put it this way, in a sort of field theory. I mean, it's not that's my worry.
We are not worried about decoherence, because in our case, decoherence does not play a role. So we measure a radiation, which is a completely different effect than decoherence. So it's an emission of some radiation out of the blue, which means that there is something which jiggles the particle, like a kind of a Brownian motion on a charged particle. Okay. So Brownian motion, which can't be neither cosmic radiation nor, so you need to have something which is, so yeah.
Okay, I see.
There are more details for who might be interested in our articles, also from mathematical, of course, derivation, because there is a section which is dedicated to mathematics, which, me being an experimentalist, I'm not the most dignified to defend it properly, but it's a very well done mathematics which calculates and shows step-by-step motivations, starting from the Lindblad equation, modified Lindblad equation, to derive the rate of the emission of the radiation.
No, that makes sense. That makes sense.
I see a question here from Pedro Alvarez, who is asking what are the other possible sources for the radiation that are not related to wave function collapse? Yeah, so that's a good question, because it helps me to tell a few things. One, which is a rather trivial thing, which means that if you see, like in our case, you have cobalt sources, so you have well-identified sources of photons, you know that, for example, that photons might also come into your apparatus like Compton radiation. So they scatter and they lose energy, so they produce a continuum tail. So that's definitely a source of radiation which you perfectly know. However, in our case, by Monte Carlo, by making the Monte Carlo of known sources, we justified 88% of the spectrum. Now, what is the remaining 12%? The most likely answer is our sources we are unaware to have. So if it is too small, you might have, I don't know, a radioactive uranium, which is too small, and I can't see it. So that's the most likely answer. Now, the other way, let's assume that at some point we measure a radiation. How can we be sure that that radiation is not dark matter, or how can we be sure that it's really collapse? That's a more complicated answer, because you need to do additional research. And that's really very, very interesting. Then you need to do experiments which are chaining and streaming it to disentangle the effect and the source. So it's a whole program which actually disentangle, once you are sure it's nothing to do with cobalt, potassium, trivial sources, which you can't pick up from your apparatus, then it starts to be very, very, very interesting, because you need to be cleverer than that to test the reason for that radiation. Meanwhile, what we are aiming is to set limits. And of course, setting limits, it's always kind of, I'm not saying easier, because experimental wise, it's extremely difficult. But logic wise, it's easy. Yeah, go with the limit. And you might assume that if you are brave enough, sooner or later, you kick the ultimate limit, and that's it, goodbye model. So you eliminate the model, at least in principle. But it would be very interesting if at some point, whatever you do, you stay with a level of radiation which is there, and you can't get rid of it anymore, any longer, and it's compatible with, for example, collapse model. That would be very interesting. But the ansatz to which you start to do an experiment, it's to lower the limit, which is also philosophical wise, if you want, interesting. You are muted.
No, just wanted to say thanks, and sorry I didn't notice Pedro's answer in chat. Good that you noticed. Yeah. Further questions?
Actually, if I may, I want to ask a question. I don't know how simple it is, but I want to clarify the difference between this jiggling that you mentioned and thermal vibration.
Yeah, so the best thing I can do is to make, that's, so we compare this with this Debye-Weller factor for germanium crystal. So we take into account the possible displacement in the lattice of the nucleus. So more details are given in our paper. Whatever vibration would be inside the matter would never ever give radiation of this type of energy. So you don't expect to have radiation out of nothing. So like in our case. It's an interesting.
It's very interesting, your work. I really like the presentation. Thank you very much.
Thank you very much. But these are complicated items because they are at the border, kind of what we can what we can know about nature. So it's very interesting.
Further questions? Further questions? Just as a sort of, since we still have a reasonable, you mentioned that there are limits on the CMB background of spontaneous collapse models, right? In the discussion with Professor Marco Cesar before. Or did I misunderstand? Because
there are limits what?
There are limits on spontaneous collapse models from the background, from the cosmic microwave background radiation. I might have misunderstood what you said.
Not to the collapse models. Oh, well, at some point, if you want to do an interference experiment with a big object, and this big object has to go somewhere. So it's not a practical limit today. Okay. Today you have other noise sources, but at some point would become. So not today. Today, yeah. That's not a limit because you fight with many different, actually, you fight, not in our case, but again, I refer to interference experiments. You fight with the vacuum. So that's the main source of noise, the particles which are residual in your apparatus because you couldn't do the perfect vacuum. So that's the main source of noise right now. But at some point, you'd go in space, there is nothing to collapse your wave function, perfect vacuum, but you still have radiation, the microwave background radiation.
Of course. Further questions? If not, thank you very much again for this great talk. I'm stopping the recording now.